the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 101, where today we are going to be talking about experimental astrophysics, experimental astronomy. Let me keep it a little simple. So the big question, right? The big question. First of all, welcome back to our episode, the recent viewers. The big question, we have been a little bit delayed for the last couple weeks, as some of you might have noticed. Mm-hmm. And it's simply been because of an extremely tough schedule at school. I think all the university goers out there, all the university listeners can definitely attest to it. You know, when you have those periods where you basically don't have a life. That was us for these last 3 weeks. So here we are, finally recording another episode. So it's very exciting for us. And yeah.
Yeah, so I guess it turns out that we were able to do this during second year. We didn't take a break during second year, ever. But yeah, third year is pretty busy this time of year. Mm-hmm. So yeah.
Also online, I was gonna say online, I think. Like the fact that we were online, like you can get out of your bed and go to school. Yeah. But here, you know, it's like an hour is spent just getting to school, like coming back and whatnot. So there's a lot of extra time that's gone there. So then now we also have a podcast to record. So it gets really hard. So unfortunately, until our exams get over, which is end of April, it's going to be like a whenever we can record, we record kind of basis. So
we will definitely release an episode after April 8th, because that's when our classes finish, and I'm pretty sure we have like a week break between classes and exams.
Not a break, but yeah.
But yeah, we'll definitely have time to do another one there. So it's not going to be like another month, but yeah.
Yeah, no, that's definitely good to mention though. At least we wanted to get it out of the way for why that happened and why it might happen again, especially fourth year. Now, I don't know what's in store for us there. So at least now that you know that this can happen, it might happen again. And it's all just dependent on our school, right? It's not like we don't want to record. It's simply the time. So we can, I think, get into it. Do we have, I'm forgetting. Yeah. I'm forgetting.
Well, we do have a comment of the week, and so many nice comments on episode number 100. But this week's comment of the week goes to Matthew Quirk. He says, wow, episode 100. I'm so happy I could be here for this milestone. And I know Parker was saying that it doesn't really mean anything because I was talking about the number. It doesn't, you know, but he says triple digits. Let's go. I'm a senior in high school, currently taking linear algebra and differential equations. I don't know how you're doing that in high school.
Equations?
Yeah. He says, I want to go into pure math, but listening to your podcast more and more makes me want to study physics. Anyways, here's to 100 more episodes.
Wow, right. What a comment.
Yeah, by the way, like if you study math, going into physics is such an easy transition because most of the time physicists learn things before they learn the math for those things. And so it's kind of like you understand what you learn the year after when you actually get into, like, we've been dealing with the Schrodinger equation since first year, which was 2 years ago. And just this year, we're learning about partial differential equations, which the Schrodinger equation is a PDE. So just now, am I really like understanding it a little bit deeper and it like actually makes sense? So, you know, if you're studying math, like pure math, you really like understand everything the physicists do, but like all you gotta do is apply it to the physical world. But yeah, so good luck with that, Matt.
Valid. Can we get into it?
Mm-hmm. Can we get into it? Yeah, I think the very first thing we want to talk about today, right, both of the things we're going to talk about today were labs that we did in our experimental
astronomy. Like it's called practical astronomy.
Yeah.
But like I think like experimental astronomy, like it's kind of more.
Yeah. So every semester we have a few labs to do, and these labs are very interesting. And,
like very interesting.
Yeah. Yeah. We're actually the one that we're doing today we'll have to talk about later because it's actually also very interesting. But okay, The first thing we're going to talk about is exoplanet transitions.
Oh,
We talked about this with Sarah Seeger, Dr. Sarah Seeger. She's an exoplanetary scientist, and we had her on episode 99, I think.
yeah, I think so.
Yeah, that was a very awesome episode. And this is one of the techniques that we spoke about. You know, how do you tell if certain stars have planets that go around them? There's many techniques. One of them is exoplanet transits. How do you detect transitions? Okay, so an exoplanet, just, back to the basics. It's a planet that is not in our solar system. It's orbiting a different star. And a transit is when that planet goes in front of that star. And of course, this is with respect to our line of sight towards that star. Because of course, some solar systems can be oriented in different directions, and maybe you have a planet that's going around the star, but never goes in front of the star, right? Like it's always, it just looks like it's doing a circle around that star.
It's like a face on.
Yeah.
That's like the face on versus like edge on
Yeah.
kind of descriptions of. So this is basically just all talking about basically what we're describing is like the planet's inclination, right, with respect to its star from our perspective.
Yeah.
From our perspective. Because remember, everything when we go extrasolar is from our perspective. Because when it comes to things orbiting the sun, it's pretty easy to, go ahead and change it from our perspective to the sun's perspective to the galaxy's perspective and whatnot, because we know our location. But when we're comparing it or looking at some random star, of which we're trying to find a planet, we don't really know its exact location in the cosmos. So we don't know its, you can kind of think of it like a spatial grid. We might know like briefly how far it is, but we don't necessarily know its coordinates. And that is kind of what's stopping us from extrapolating exact values with respect to the star. So it's always, with respect to us, we see that the planet's inclination is 0, which simply doesn't mean the planet is actually, perfectly level with the star. It's actually the opposite. It actually means that we don't see any transits at all, right? Because it's completely face on with respect to us. So it's all perspective when it goes extrasolar.
Yeah. Well, I'm not sure what you meant by we don't know where the star is, but like we definitely know like where it is.
Like we have its coordinate, as in like we understand where it is.
But
in the
also
night
like
sky.
we can kind of like if it's far away, we can kind of there are ways to tell.
No, because I was mainly thinking about I'm kind of getting ahead of the whole thing.
Like the
but
distance ladder.
No, I understand that we know where it is.
We know the direction and the distance.
My question, my main thing is simply by extrapolating, like planetary properties, we can't put it with respect to the actual stellar system. It's always with respect to us, is what I'm saying.
Okay.
Right.
Yeah, okay.
Like if the planet is completely edge on, which means like it's. Wait, is that inclination 0 or did I mess it up?
No,
Sorry.
yeah, that's right. That's right.
Okay.
Yeah.
So when the planet is edge on, that means it's perfect. Like we are perfectly in the line of sight of the planet. Then what happens is, in this case, again, all of the information that's extrapolated is all what we are seeing. We won't be able to convey that inclination to the actual inclination of the planet around the star.
There is no actual inclination, you know what I mean?
Well, I mean, the planet is inclined with respect to the star's orbit, but
that's what you mean. But that's two different things.
No, exactly.
Like
that's
those are two different things.
That's the whole point that I'm trying to make, that we can't get the true values with respect to its star because all of our measurements are done from our perspective, right? And that's just like one limit of this whole method.
Okay, yeah.
Right.
Yeah, sure. But those things aren't really relevant. Like the inclination of the pole of the planet
is a different
not,
inclination. But I'm saying,
but it's not relevant to like the detecting the planet.
Oh,
right?
no,
You
of
know
course
what I
not.
mean?
No, not at all. That's why I said I'm getting ahead of myself, because I'm going into the next thing that we were trying to talk about.
Oh yeah.
Yeah, exactly,
Okay.
exactly. So that's exactly why I said that.
That also doesn't have anything to do.
No, but I'm saying we can't do that next step because of the fact that we are looking at it from our perspective. You feel me?
But I think you're talking like, are you talking about the inclination of the pole or the inclination of the orbit?
I'm talking about, we know the inclination of the pole. We can't find the inclination of the orbit
How do we know the inclination of the pole?
Because that's what we're seeing.
The
Or
inclination of the orbit.
Am I messing?
The
Sorry,
whole
I'm flipping
orbit.
them. I'm flipping
Yeah.
them. Am I not? Yeah, I'm flipping them. Sorry.
Yeah.
Sorry. We know the inclination. Sorry. We know the inclination of the orbit. We don't know the inclination of the pole, and we can't find that out because of the fact that we are looking at it from a perspective. Right. That's just the major point that I kind of wanted to bring on the table.
Okay. I think you're also confusing with something else, but we're gonna get to it later.
This whole thing will make a lot more sense when we talk about the next thing. So let's just continue with this before I got very much ahead of myself. My bad.
We were talking about, what was I even talking about?
Once you just
So the planet goes in front of the star. We can tell that there's a planet there. How do we tell that? Well, the star has a certain flux, and a flux is energy per second per unit length or unit area. And energy is in the form of photons. We see photons coming. How many photons per second per, how big the projection of the star is on the sky. Or I guess another way would be to say, like, the way we calculate flux from the moon or something like that is we say like the way that our prof kind of explained it was like, if you take 1 meter squared where we are right now, and you say how many photons pass through that 1 square meter per second will be the flux from that source right there.
Now, an interesting comparison to, you might be wondering, okay, I understand how to do it with a ground. How do you do it with a telescope? Well, you have a pixel, right? So the flux that is measured in a camera, in this case, if let's say, as you were mentioning, like, how do we know that there's a star? Well, we know there's a flux. So measuring the flux through a telescope is actually very similar. We already know the dimensions of the pixels, right? Because that's just simply given by the detector or camera that we're using. And all we really need to do is simply measure the number of photons, or, you guessed it, just brightness of the pixel. So measuring the brightness of the pixel compared to the size of the pixel gives us a reading for the flux.
And since every pixel on your camera is the same, you don't really need to consider the size of the pixel. And so, a measure of flux is just the brightness of the thing on your image.
Exactly.
And, it's not exactly like 1-to-1. Like, the flux is not, the actual flux of the star is not equal to, how bright your pixel is, but it's like literally proportional. So that's why we take the brightness as a measure of the flux. So the star is sending photons our way, and photons are coming from every part of the star, and we're going to get to a little bit more in detail about that. But right now, let's just assume that the entire star sends the same amount of photons our way, no matter where you are on the star. So it's like just a circle.
It's uniformly lit.
Right. It's a uniformly lit circle sending photons our way. Now, if there was an object that were to pass in front of that star, that object would be blocking photons. And so by definition, it's removing from the flux that we receive here on Earth. So if we were to take a picture of the star, now because the star is really far away, it just looks like a little dot on our screen. But that dot will suddenly get a little bit dimmer when something is blocking the photons from reaching our camera. And then once that thing passes the star, it will return to its normal brightness. And that's what we detect. We detect the star literally sending less photons to our camera, and then, going back to normal, and we say, oh, well, obviously something has to be passing in front of it for it to dim. And so we say, there you go. There's an exoplanet, and it is transiting in front of the star. And that's what we did in our lab.
Now, yeah, sorry.
It's a little bit more complicated.
Yeah, I was just going to say, it's very easy just to understand the theory, because it's, well, if something is passing by it, well, obviously it's going to dim by some factor. And interestingly enough, that factor is also related to the size of the planet. So that's actually how we computed the radius of whatever planet is transiting the star. But now the problem is kind of twofold. The number one is actually number one leads into problem number two, and number one is, well, does the star stay constant, number one, in brightness, so that we can simply measure this planet transiting?
Because there are variable stars that their brightness literally changes on dynamical timescales, which is not that big compared to other timescales. We spoke about timescales in the previous episode. Yeah,
I know we definitely
in the astrophysics episode.
Yes,
basically,
yes.
The dynamical timescale is much shorter than something like the thermal timescale. And so, you have these stars called Cepheid variable stars, and I think maybe we spoke about that. But anyways, Cepheid variable stars, their brightness, the period at which their size changes is proportional to how much the brightness, the luminosity.
Yeah.
So
Pure luminosity relationship with Cepheid stars.
because Cepheid stars literally, their radius changes.
Yeah.
They puff in and out, and the size is proportional to the luminosity, or there's some power relation there. I guess, the details don't really matter. So that star literally is intrinsically variable. And so if we were to assign, that variability in its brightness to an exoplanet, we would just be wrong, because that we would have to be more precise. We'd have to kind of cancel out that variation. And this is such a cool lab. There's so many things to say. But yeah, once we get rid of essentially the intrinsic variation, then we can tell if there are outside sources of dimming that come into play. And so the number one source of variation that we found, right, is actually the sky. Because the data that we were analyzing came from a telescope, actually the William Herschel telescope. And unfortunately, the telescope is actually on Earth, meaning that it has to look through the atmosphere. And the thing about the atmosphere is that it scatters a lot of light, even at night. Even if you're in a very unlight polluted place, it always has some effect on the light that passes through the atmosphere. And what we noticed, right, what we had, our data set was basically just like 300 3 to 400 images throughout the period of like 3 hours. So it was about one image every like 40 seconds. And we found the brightness of the stars on the image and just plotted it versus image number. So we had these light curves, which was just how bright is it.
Light curve is it's a very important phrase.
Yeah, very important.
Like, light curve is like the professional way of saying, okay, what we're getting is its flux versus time. Now in this case we did image number, but you can
it's the same thing.
It's basically analogous to the
because
time.
An image was taken at a certain time. If you just convert image number to time, then it's right. It's flux versus time. So how is the flux that we see here on Earth changing in time? And we can do this for, we didn't take the pictures, but in the pictures there was a bunch of stars, and we found these light curves for as many stars as we could on this image. And it turns out that from, without correcting the light curves at all, we can literally see that they follow a certain pattern. There are outliers, obviously, like Cepheid variable stars or other stars that just kind of do their own thing in terms of brightness versus time. But most of the stars that are like main sequence stars are just stable stars that have a pretty constant flux. They follow like this very not constant, but they're all proportional to this one heavy variation factor, which actually turns out to be the sky variation, how the sky changes the brightness of the entire image. And that's why all of the stars follow this pattern. And so how do you get rid of that? Well, all you got to do is divide the light curve by that variation.
Yeah, it's important that all of them follow the same pattern, right?
Yeah.
Because all of them are affected by the same thing. Because the problem is, if let's say you're interested in a Cepheid, this whole method kind of breaks down. So when you have these variable or these stars that are not supposed to be variable but are somehow variable, and all of them are just somehow variable, you can well be like, okay, well, they all have a common factor of variability, right? So given the fact that all of them vary on this order of magnitude, if we simply divide out all of that variation, basically in a way, what we actually did was by taking the median of all the light curves on each image, which is basically taking the variation of each image and just dividing the whole thing, each light curve, by that variation. What we're basically doing is dividing each star by the sky variation, right? And that's exactly what we wanted to do in the first place. Because the sky variation is unfortunately quite a big factor that plays into quite a few things, which is why primarily all of these experiments are done from outer space. This episode of the podcast is sponsored by Brilliant. If you've liked any of the stuff we've been talking about so far, I mean, you're already here, aren't you? You must enjoy these courses. Brilliant offers a very interactive way to approach a lot of programs, a lot of question answer, a lot of practice base. So we kind of like that about them. And interestingly enough, they have a whole section called Worlds Beyond Earth, where they talk about exoplanets and, in particular, transits. It's exactly what we're talking about in this episode. So if you enjoyed it and if you want to know more about it, always good to know that the first chapter of every Brilliant course is completely free, just for you to go and check it out. And if you do happen to enjoy it, enter the code MPP or simply go to brilliant.org/MPP for a 20% discount on your premium subscription. Go check them out. Now back to the episode.
Here's a good example, actually. Like, all of these curves had different brightness levels, right? Because some stars are just brighter than others from our view here on Earth. So some of the stars were low on the graph and had this variation, and some of them were higher up, and then we're following kind of this same pattern. But the idea to take away is that every star, every stable star, is proportional to the background variation. And so let's say you have one star and you have three images, right? The flux goes like 1, 2, 3. And you have another star that goes like 2, 4, 6, right? So you can imagine kind of plotting 1, 2, 3 and then 2, 4, 6. So these two stars, if we assume that they're just stable stars, the flux that we receive should be constant, right? Now, the common ground here between the two is that we see that the brightness goes up at a constant rate. And so if we divide each of these light curves by their own values, like 1 divided by 1, 2 divided by 2, 3 divided by 3, that's what we mean by dividing out the variability, is that
that's normalization. That's different.
No, I mean, like, that's the variation that we take out. Like, we also divide the second one. We do 2 divided by 1, 3 divided by.
No, it's the other way around though.
Or 4 divided by 2.
When we divide 2 by 2 and 3 by 3 and all that, like, that's normalizing the curves.
Okay, no, like, I'm just saying, okay, but instead of taking the median, you just take it to be the first one, right?
Okay,
it's all the same thing, because
Yeah.
median just moves it up by a constant.
Yeah, of course.
Okay.
Yeah.
So by dividing, the first one by itself, then you get just a normalized curve. But if you divide the second one by the first one, assuming that the first one is like perfectly.
Oh, assuming that the first one is okay.
Yeah. So you just do like item by item division, and that's how you get a flat curve. Now, I don't think we need to talk about how to get like a good approximation for the sky variation, but that's basically the idea, right? The idea is that the stars follow a certain pattern. We kind of find that pattern and then just divide the curves, just flattening them out so that we get an idea of how we get a better picture of how they actually are, which is mostly just flat.
Exactly.
But now the issue, I guess it's not an issue, it's a good thing. There's one star in the image that we knew which star we were looking for, by the way. We weren't
Yeah,
just,
so this
we
is
weren't
actually
just guessing.
Yeah, this is an important thing though right here, that we knew which star we're looking for, because in a true experimental case, you would not at all be conducting this experiment from the ground, because it would be nearly impossible, because then you would have to correct for all this stuff and then look at what we do. We don't do this, but what telescopes such as the Hubble does, right? Then Hubble is actually famous for its detection of exoplanets. It does exactly this, but in the sky. So I mean, in space. So without the whole effect of sky variation. So in this case, you're nearly getting the intrinsic variation of the star. So by basically compiling like hundreds and thousands of stars, Hubble is able to see the ones that dip enough to make it such that it might be an exoplanet. Because interestingly enough, like the Earth, for example, if you look at the Earth, now I don't know the number for this, but if you look at the Earth dropping, like the light curve of the Earth, it's almost negligible, right? Like it's almost like there was nothing there in the first place. Like the Earth, the amount that the Earth dips because its radius is so tiny.
The sun dips because of the Earth.
I mean, sorry. Yeah,
that makes a little more sense.
That's what I meant. Sorry, my bad. Sorry, I'm talking about the sun's brightness dropping because of the Earth passing by it. I'm saying that drop is so tiny because of Earth's small radius compared to the sun. However, planets such as Jupiter, who is like 0.1 times mass, times radius. I don't really know. I forget now, but I think it's 2%.
I think it's 1%, maybe 1%.
Anyways,
or the volume.
A big value,
I don't know.
For a radius. If a planet has a sufficient enough radius, that means one that, again, I don't know the exact value, but there are like 1 to 2% deviations in its light curve, then they are more likely, or obviously, to be seen. So planets such as Earth hardly even get detected because they are so small. But planets such as Jupiter, they're actually called hot Jupiters, are one of the most famous planets that we detect because they're so easy to detect, right? Because
because they're close to the star, which means that we can actually detect transits not that far apart, right? Like because of Kepler's laws, right? So the closer you are, the faster your period. And so some of these planets, like I'm pretty sure the one that we found had a period of like under a day.
It was
like
so fast.
It was crazy.
It was so fast.
So,
1.4 days orbital period.
Yeah, so you can literally see the light curve for this exoplanet every single day. And so that's just further evidence that like, oh yes, this is actually an exoplanet.
So it's a very powerful technique, that we just used by ourselves, that is actually computerized and then used by, very, very, very high sophisticated systems. Because, I mean, if you think about it, like that's basically what they're doing as well. They're just like, taking the background and subtracting all that and then looking at each star individually. Because an interesting thing, and this is, I don't know how much this plays into it because we didn't really discuss it while doing our lab, but extinction, like gases in space.
I guess for this lab it wouldn't really matter
because we're talking about relative, right? Because we're talking about relative
fluxes.
Yeah,
and also it's like we're looking at like one star and we're analyzing the curve for that one star. So like the intrinsic flux, or like the apparent magnitude versus the intrinsic magnitude, like but we're not really concerned about
either
that,
way,
right?
Like it doesn't really affect our measurements because in this particular experiment we are looking at the relative values, right? So it doesn't really matter if there's more or less extinction because that doesn't change the relative values, right? Yeah, that's technically right. Also, extinction, I think we've talked about this before, right? It's just dust. It's just what happens when light goes through dust in space. There's a lot of dust in space, by the way. So when light happens to pass by this dust, some of it's absorbed, some of it's transmitted, and some of the dust itself heats up. And this heated up dust now starts to emit its own light, right? So now we have to actually correct, or not necessarily correct, but just know that, hey, this effect actually takes place, right? So that's one thing, not necessarily relevant to this particular experiment, but I was just thinking that it might have something. It doesn't really have anything.
Are you thinking about circumstellar dust, like in what we're doing in our most recent lab?
Yes.
So yeah, the dust that's like in space wouldn't actually heat up enough to like emit its
Yeah,
own
but I'm
light.
talking about like around the star.
Yeah,
and
so
whatnot,
yeah,
right?
so
Exactly,
not just
exactly.
dust like in space, but dust like that's close to the star will be heated
Would
up.
be
Yeah.
heated up. Sorry,
Yeah.
that's more correct.
Yeah.
Yeah.
But yeah, that's right. All that about extinction.
What's our next step? Now that we have our curve.
Well, yeah. So once we
have a
have
curve
once we have
yet?
the sky variation,
Yeah, once we have our
and we
sky variation.
divide the curves, we know which star we're looking at. By the way, which one has the exoplanet? Then we isolate that curve of the star we're looking for. We divide out the sky variation, and just like magic, we get a very nice straight line, a dip, and then it comes back to a straight line. And it's like, wow, okay, we have identified the planet transit. Now that we have like the actual dip in the light curve, it's time to analyze that dip, because there are a lot of things that you can deduce from just that transition. Okay. First thing you want to do is normalize the light curve, which means that we're talking about relative flux. When the flat part of your curve is equal to 1, we're talking about units of stellar flux, right? So the star that you're talking about emits a flux of 1. And then anything that gets in the way will be reducing it by a certain percentage.
So technically, this step isn't required. It's useful, but it's not required.
To analyze.
No,
right?
because even the radius and all
Yeah,
that stuff is given.
sure.
Yeah, technically,
Sure.
like the general formula that's used doesn't use relative
Actually,
flux.
Yeah,
No, it
yeah,
uses
no, I
delta
guess
F
you're
over
right.
F,
Delta
so it
F
doesn't
over F,
actually
yeah,
use
it does.
relative flux. So if you think like it helps to see it a lot.
Sure,
You know, because sometimes like if it's also like 500, like a 1%. No, I guess a 1%. I guess the percentage would be.
Yeah,
the percentage
would be the same. Yeah, exactly.
But would the dip show as much?
Yeah, it would.
I guess
yeah,
it would show
your,
the same,
your,
right?
the axes of your graph would
so
be.
I guess nothing would really change.
No, nothing would
except
change.
for just understanding its. I mean,
I
nothing
don't know.
really would
I
change.
guess it's just percentage, so we're dealing.
Yeah,
with,
I mean, it just because remember, it's all about proportionality, right? Because we're saying that the amount that the light dips is related to the size of the planet.
Yeah.
In relation to the star,
yeah.
of course.
Because
In
imagine
relation to
the moon, quote unquote, transiting in front of our sun, blocks a lot of the light, right? Like almost all of it.
Yes,
almost.
exactly.
Right? That's because, I guess we can't really compare it to a planet
not a
that's
very good,
orbiting,
yeah.
but from our perspective, it's a very big planet that's radius is very similar to that of the sun's, and that's why it blocks all of it. But then a smaller object passing in front of the sun would block less of the light, and so we can therefore, say, I think it's like the proportionality is radius squared, right? So the percentage by how much it dips is proportional to the radius squared of the planet over the radius squared of that has to do with projected areas onto the sky. And by the way, I hope I didn't confuse anybody, but in the case where we're looking at a star that's very far away from here, we actually don't take into consideration how far away the planet is from the star in terms of the radius calculation, because technically the further away the planet is from the star, the bigger the effect is, right? Because imagine you have like a big star and a small planet, but the planet is really close to the star. Then it would almost seem like just a little piece of dust, right? But then imagine the planet is like super, super far away from the sun.
like almost close to you.
Yeah, almost close to us. It would literally block more than the star. So, but in this case, because these stars are just so far away, like this effect, like if a planet is gravitationally bound to the star, really this distance compared to how far the star is actually from us is so negligible that we don't even consider that effect.
Yeah.
Yeah.
What's next? Now that we have, what do we have right now?
Radius. I guess a lot of the other stuff that we calculated isn't really relevant because we had to go and take data from an actual catalog. But something else that's pretty important to mention, and that I said we were going to talk about more in detail, and now is that time, is something called limb darkening.
Oh.
Because in the very beginning of this podcast, I said, let's just assume that our star is a disk uniformly lit, sending photons our way. And it just so happens that stars just aren't like that. That's not how they are. They're actually brighter in the middle and dimmer around the edge of the star.
This is simply, I mean, we can explain it quickly. This is simply because of how, well, the core and like, what are we really seeing when we're talking about a star? So the thing is, when you're looking at the center of a star, well, what you're seeing is, in fact, the photons from the very center. That makes sense. I mean, you would essentially want to see the photons from the very center in all cases. That would mean it's completely uniformly lit. However,
Projected center.
Right. Always project. I'm always
because
talking about
the photons come from like the last collision basically is in the photosphere, which is not as hot as the center, which means the photons are like lower energy, right? Like the black body spectrum only depends on the temperature of the photosphere and not the core, right? So when we're talking about, like, when we say center, we mean like, okay, you project the star onto like a two-dimensional thing in the middle of the circle.
Yeah, technically, yeah, it's not necessarily, yeah. So that's how we're dealing with it in this case, at least, because we're just trying to keep it simple. So having that the center is, in fact, very hot, and the photosphere, or like the outer layers of the star, is very, very, very much colder. I think the difference on the sun is like three order magnitudes, right? It's
1,
like
2,
10 to the
3.
6.
10 to the 7 in the middle.
10 to the 7 in the middle, 10 to the 3, 10 to the 4,
3, 10 to the 4.
in the photosphere. So quite a large difference in the temperature itself. And that temperature difference is actually what causes this whole effect. Because what we see is on the limbs, quote unquote, of a star, which is basically the edges. When we're talking about the edges of the star, the core is, how do I explain this actually? I'm actually thinking about the diagram, and I'm like, it's so much better just to draw it.
Yeah.
But
well, it's like,
maybe
essentially our line of sight, if we take our line of sight and we look at the middle of the star, it's pointed towards the hotter regions of the star. But as soon as you look away from the center, you're kind of piercing the colder regions of the star, which is like the outer regions. And so we receive like lower energy photons, and actually less of them because it's like thinner, you know what I mean? Like the optical depth.
Less energy photons, also why this whole thing happens, right?
Mm-hmm.
Why we get this lesser brightness, I guess. Because in a case where this is not true, if the star would be completely uniformly bright, then when the planet transits, what we expect is from the moment it's... Okay, now these are, I guess, two terms that we can also explain, because I guess it is important for transits, and it's called the ingress and egress times. It's just two words. You probably will never remember it again. But basically what they represent is the position. So ingress is when the planet is completely inside of the star, with respect, again, from our perspective.
Yeah. Well, ingress is like the period of transition.
Yeah. So
being out to in.
I mean, ingress is like, yeah. So you can say that the time it takes. And the egress is when it's basically just leaving the star. So one side of the planet has just entered, you come into the ingress times, and the moment the other radius, like the other side of the planet, touches the outer radius of the star, again, with respect to us, we call that like the egress time, right? Wait, why was I bringing this up again? Oh, yeah. So in the case of no limb darkening, we have in between these times, we have, well, generally, it would just be a flat curve, right? Because the brightness has dimmed by some factor, and assuming that the star is uniformly bright, it should dim by that same factor throughout the planet's transition.
Yeah, but
That's
now
not what we see.
Now it depends on the inclination of the planet. Because let's say the inclination is perfectly 90 degrees, which means the planet passes through the middle of the star. That means as soon as the planet touches the outer radius of the star and starts to transit in front of it, it will be first transiting in front of the dimmer limb areas of the star, and then it will keep dimming more and more because it's going near the hotter regions. It's covering up the higher flux regions.
By the way,
star.
the planet always goes through the middle of the star. Like
No.
like even in an inclined or like no matter how your orbit is, like with respect to us, like it's like what do you mean middle of the star?
No, so basically the inclination is with respect to our line of sight.
Yeah.
What is the inclination of the orbit? Okay, which means that when the orbit is inclined a tiny bit, it'll just pass over the top part, right? See, when the orbit is inclined, it'll just go over the top part of the star, which means that this is when the limb darkening effects become important, because out here it'll never actually get to the full brightness of the star.
Yeah.
Right. So if the inclination is, let's say, like a couple degrees, and the star only covers up, let's say, like the very top, like couple percentage, right, of the star, then it's only covering up the dim parts of the star, which means that our model fails dramatically, because our first model assumes that the upper parts of the star are illuminating our camera the same amount as the middle parts of the star. And so we will be predicting that it actually, like, the dip should be a lot deeper than it actually is, versus what we actually see is just like a tiny dip because the flux that it blocks is not that much compared to other parts of the star. Yeah.
So we correct for this by using the limb darkening model, right? So it basically, I mean, we don't obviously I don't even think we really understand that model, but it's a pretty sophisticated model.
I mean, mathematically it's pretty easy to understand, but the thing is that there are different models to actually explain this. There's, we used a quadratic model, which just means that there's 2 degrees of freedom. There are other models, like, I know there's like a logarithmic, exponential, all that kind of stuff. And it turns out that one model is not better than the other. I think they all have their strengths.
Depending on, I guess,
Depending on your star.
Yeah, depending on your star, depending on your planet, I'm assuming too. And these are all so powerful because through this simple measurement of radius, now, we didn't actually do this in the lab because it was actually significantly harder, but you can actually do a lot of more things through the radius measurement. Having the radius, you can compute the period because it's constrained, right? And then you can...
Yeah, but this ties into a lot of other quantities in the orbit that we didn't talk about. Like the impact parameter and that kind of stuff.
I guess you're right.
But yeah, that's pretty much like the core of exoplanet transitions.
I mean, the whole core is just finding the radius of the planet. That's
finding the light curve, seeing the dip in the light curve, finding the relative flux dimming percentage, and then from there you can infer different properties about the system.
We didn't even talk about astrometry, man. I'm just thinking about that now. But I do want to say something though, that these two things are called important things. So astrophotometry is actually, so the things that we did in this case is actually astrophotometry, is the astrophysics of dealing with images and dealing with photons. Photons? Photons. So we actually did 2 types of photometry in this experiment. We did aperture photometry, which is basically simply looking at a singular star and computing its flux. So the whole act of computing a flux of a star is called aperture photometry. Very fancy name for it. And then when we compared all the stars, we call that differential photometry, because what you're doing is when you have the aperture photometry, like when you already have this done for multiple stars, as we were talking about dividing the variation and whatnot. So that's basically differential photometry, the second part of it, where once you already have all the apertures, you now divide it out by the variation. So, I mean, kind of just assists what we've already spoken about, not really adding anything new. Maybe you can search it up in your own time. There are actually very interesting ways to do it. Also because this is exactly how telescopes and supercomputers compute things. So it's a little interesting to say, hey, we just did a simplified version of that. Because remember, in our case, also one thing that you have to always account for is the fact that these stars are moving, right? So when you're taking 300 images across 3 hours, you have to remember that in your night sky, these things aren't constant. They're moving because the Earth is moving. So now you have to take into these extra effects where you actually account for, added variation in the fact that the Earth is moving. So it's just small things here and there that we must pay close attention to. But apart from that, that's basically the essence of finding a planet, right? Like, how cool is that? I think that's really cool.
Yeah.
When we found the light curve, I just remember you screaming, because it was so satisfactory.
I mean, that was mostly because we were in a time crunch.
Okay, maybe not necessary to say. Maybe not necessary. But the importance is that when we found the curve, it's a very satisfying experience, because I think just relating that to groundbreaking physics, because what are we doing? The things that we were speaking with Dr. Sarah Seeger is literally this. We still don't know which of these planets have, proper like life forms or whatever. Like, that's our next step, but that's a step so far away we can't even see the line to cross. So all we're doing right now is just cataloging all the planets that we can really see, all these exoplanets that we can really see, and then, differentiating them with respect to mass and radius. So then we can one day, when we finally, let's say, have some sophisticated technology to, determine life from atmospheric composition or whatnot, we already have a huge catalog of planets to test, right? That's basically the goal. Now, unfortunately, we have a class in the next 20 minutes, and we have something else we want to talk about.
We can mention it briefly.
Though, I was gonna say next episode, but you want to mention?
No,
this?
we can because it's not.
I mean,
the thing about this lab is that there's not much that we can explain. We can explain what we did in the lab, but essentially the details of the lab is a lot just in the actual equations.
No, but I wanted to talk about the variables. Like, I wanted to talk about the longitude of ascending node.
Oh yeah.
Inclinate. Okay. All these variables with basically.
That's true.
Quick rundown, because we mentioned it in the beginning of the podcast, where you might have got confused, where we're just talking to each other, where these variables. So basically what we did is, using observations made on Earth, we converted those observations. Now, this is a planet that's orbiting our sun, so it's much easier. Using observations we made on Earth, we converted this to observations with respect to the sun. And this is basically the essence of our lab. That was basically the big one. And with now having the motion, quote unquote, there are a lot more things to actually do, but having the motion around the sun, we can now deduce a bunch of parameters of this object. So what we just did is took telescopic images, just pictures, like 2-3 pictures from your telescope. Obviously, you need, I think, a minimum of 3. No, yes,
yeah,
a minimum of 3.
Because you need
a minimum of 3.
6 degrees of freedom.
Exactly. You need a minimum of 3 to get the acceleration. So basically to get the proper motion of the object. So just with 3 images, you can literally deduce the orbit of anything around, in this case, our sun.
Yeah.
I think that's very impressive
the degree of precision is very questionable, but you can still do it.
There's definitely a lack of precision with a lot of uncertainties and
I think that's mostly us, our...
I don't know. Okay, yes. Also because we're, very, very unsophisticated in comparison to what, again, these telescopes do automatically, right? Like, these telescopes will take 4 images separated and automatically compute the whole thing, and it's already done. Because all of these can just be put into one Python script.
And also, it's already been coded by smarter people who know what they're doing. So as soon as you get and even telescopes can take more than 3 images, right? And the more images you have, the more constraints you have on the orbit. So the more precise it'll be. So,
So just different things. Maybe I think we should definitely dedicate an episode to just talking about these variables, because it's important in 2 reasons. Talking about different coordinate planes, right? We have 2 major ones, which is the which is the ecliptic. No, sorry. Two, not coordinate planes. Two reference objects, basically. Basically what I'm saying is heliocentric and geocentric coordinates. This is very important to the whole lab. Heliocentric is centered around the sun, and geocentric is around the Earth. So this conversion between these two is very important, that I think we can literally dedicate a whole episode to, as well as dedicating it to talking about the individual variables that actually impact the orbit. So there are 6 orbital parameters that basically dictate your whole orbit. You have these parameters, you know everything about an orbit. So, and they're pretty significant. So I was thinking maybe we can do it at the end of this, but I don't think the time exists.
No.
So we can definitely push it to a future episode.
Well, all right.
Thank you so much for listening to this podcast. It was definitely an enjoyable one for us as well. Definitely after some time. So we'd like to thank you for keeping up with us. Maybe a little rough in the beginning, but we'll always get there.
Mm-hmm.
And
Yeah, well, we will be back. Don't know when. Hopefully next week. We'll see how things go.
Next week will be tough.
No, next week will
No,
definitely
maybe
be
not
tough.
next week. We'll try, but chances are very low.
The thing is,
Chances are low.
every single week, we literally have one thing due in every single class and on different days of the week. So it's we're never actually not doing anything.
It's so crazy. It's so crazy. It's just so crazy. I can't even begin. And on April 8th, the last day of classes,
we're just done.
No, but the thing is that I think this is for you too. I think this is for everyone. All of my stuff is due on that date. Every course that I have, all 6 courses, has something due on that day.
Not for me.
So it is just miserable. It is just miserable. So after that day, it is going to be quite a lot more calm for the both of us.
Yeah.
So after that, yes, for sure, episode will be coming out. But before that, again, we'll try, but no guarantees.
But during the summer, it'll for sure be.
In the summer.
Oh, we could talk about what we're going to do during the summer. You got rocket stuff.
Yes.
You
First
know
of
what I
all,
mean?
yeah.
Yeah.
Oh, first of all, what do you
Yeah,
mean? Oh,
yeah.
yeah. Our summer episodes are going to be really fun too.
Yeah.
Also because we're going to have a lot more time. And also a quick note about, we didn't actually mention this. I'm remembering this now. All of the giveaways that we have, NFTs, books,
We forgot
all
to
the
mention
stuff.
that.
Yeah, all the stuff. We're going to do it after our exams. There's just no way we can handle the logistics of this right now.
We just have to bring it back to the basics,
Yep,
exactly. It started off by just us talking about physics, and, we just got to tap into that for now.
For now.
And,
It'll come back. Just
in the summer, we're going to organize all of our giveaways, all of our merch, all of our...
we haven't done merch yet.
There's just so many things to keep
merch
track
was
of.
announced in December, and we just
literally
since December we've just been busy. We just had no time.
Anyways.
It's really crazy. But anyways, I hope you can understand. I'm sure you do. Anything else?
All right.
I think that's it.
Thank you for listening. We will
Thank
see
you.
you guys next time. Bye, everybody.
Peace. Okay. By the way, I didn't mention this.